Good morning. Before we start, I noticed that there are still a large number of students who didn't sign for mastering physics. The first assignment is due next Sunday, which is the introduction to mastering physics. So please make sure to complete this step today if you can. It turned out that there are several versions of the access code available in the market. Some of these codes are not suitable for the copy that is linked to Blackboard. Luckily, we have the other section, the unlinked section. So it's hard to tell which is which. But once you have your access code, first try it with the section that is linked to Blackboard. If it worked, good for you. If it didn't work, said invalid, for example, then please use that same code with the other section, and for sure you will be able to get into that section. I have several communications with many of you during the last 48 hours, and that has been the experience that myself and many of you learned about the access code for mastering physics. Another problem that I'd like to mention is the cost. It's okay to use the 6th edition instead of the 7th edition. After all, the homework is in mastering physics. So what's important is the material, problem numbering, etc., which is the main difference between 6th edition and 7th edition. This is not a problem for us. So if you have, if you'd like to save some money, it's okay to go 6th edition. It's okay also to go to used copy or to go to rent copy. Okay, there are all kinds of options, and I hope at the end, every one of you will find the option that is suitable for him or for her. Excellent. We move on. What we learned so far. We learned that I'd like to use a laser pointer because I noticed that the recorded lecture did not show the pointer last lecture. So what we learned so far is that charge is an intrinsic property of matter. Wherever you find matter, you will find charge, just like mass. This intrinsic property can be positive, can be negative, and can be neutral. The association of these three possibilities with the particles inside matter, inside the atom, positive charges are associated with protons, negative charges are associated with electrons, and zero charges or neutral are associated with neutrons. We learned that different charges attract each other, while similar charges repel each other. We learned that to charge an object with electricity, you have three different methods. Some of them works with certain materials, while some others do not work. You have charging by friction. This is simply rubbing one material against the other. You end up with transfer of charges from one side to the other, and this way, the one that gains more electron will be negatively charged, and the one that loses electrons would be positively charged. The other method is charging by conduction, and this is suitable when you have metals. It doesn't work with insulators. And the third option is charging by induction, and this works for conductors as well as for insulators, as I will explain in a few minutes in this lecture. The last thing that we learned in the last lecture is the classes of materials. We defined conductors as those materials that allow the motion of charges easily. Examples on that: metals, all metals, ionized air, ionized solutions, electrolytic solutions. Then the other class of materials are the insulators. Insulators do not allow charges to move freely within them. In this class, you have glass, rubber, PVC, wood, pure water, pure air. All these are good insulators. But if you take ordinary water, it is not a good insulator, because there are some salts, usually small concentrations of salt in water, which makes water conducting. Though it's not a great conductor, but again, it's not a great insulator. However, if you deal with distilled water, purified water, yes, that is an insulator. The third class of materials that we talked about is semiconductors. And here the conductivity is somewhere between conductors and insulators. And this is a very important class of materials. Mainly, we have silicon and germanium. And these materials are the raw materials that are used in all kinds of semiconductor technology, digital technology. Applications are everywhere around us: computers, TVs, cellulars, etc. We will learn about these devices later in the course. Now, I need to check your understanding. So we will start the first session for clicker. I will give you 60 seconds. So please read this question and click the right choice. As I said last time, if you get the right answer, you will get full credit. If you missed the right answer, you still get half the credit. So you have 35 seconds to go. Okay. The right answer is C. All have the same charge. Now, the argument to get to that answer, for those of you who missed this problem, was as follows. The green object repels the purple object. This means they are identical. They have the same charge. And then the green here, again, repels the yellow. This means, again, they are identical because of this repelling force. Therefore, we conclude that they are all identical. Second question. Read the question, and I will start clicker. It's okay to discuss with your neighbor. That's fine. This is the idea. So feel free to discuss the situation with your neighbor. So most of you selected B. I am sorry, guys. It's not B. It's negative or neutral. If it's negative, obviously it will be attracted, but also if it's neutral, by induction, the negative charges will be attracted closer while the positive charges would be kicked away. So the object now will be polarized. The total charge carried by this object remains zero, but this zero is split into two halves, one negative and one positive. So it's possible that the object is neutral and it was polarized by induction. Okay? Also, it's possible the other option that it was negative from the very beginning with a net charge negative. Excellent. How do I know what? It's not touching in this case, but I know it's negative because of its attractive behavior. It is attracted to positive. Anything that is attracted to positive must be negative. Okay? Yeah, I cannot tell. Yeah. I mean, there are other methods that we will learn later which allow us to measure the charge. That's another procedure. But at this stage, we are just trying to determine what kind of charge is there. So the correct answer, it may be negatively charged or it may be neutral. Either way, it will be attracted to the positive charge. Good question. Thank you. This is how non-conductors may be charged by induction. Non-conductors, if you dig deep inside non-conductor material and molecules, as I explained last time with water, the distribution of charges in the molecule will be inhomogeneous. In other words, the center of the positive charges does not coincide with the center for the electrons, the negative charges. Because of that, if you act on this non-conducting material with this positively charged rod, it will act on every single molecule, and the molecule will rotate local rotation. This is non-conductor, so charges are not allowed to move free motion. However, it can rotate locally. The molecules rotate locally, reorient themselves such that the negative side will be closer to the external positive rod, while the positive side of the charge within every molecule would be repelled as far as possible. As you can see, the end result, now you have a polarized object, an object which has negative charges from the left end and positive charges from the right end. This is the idea behind charging non-conductors by induction. We move on to one application of charging by inductions, which is the so-called electroscope. Electroscope is an important simple device that we use to check on charges, to check whether an object is charged or not. Initially, we have two thin and light gold leaves here. Usually, they will be touching each other. However, when you apply a net charge here at this end, because identical charges repel each other, the two leaves will spread apart. And the angle between the two leaves is proportional to the amount of charge. So this is some kind of a qualitative measuring tool to tell us whether there is charge or not and how much this charge is. Okay? I'd like to show you a demo.
An electroscope is a device used to detect electric charges. If we induce a charge in a
Okay, so this is the electroscope, and this is simply a rod and a piece of cloth. And now,
device used to detect electric charges. If we induce a charge in a rod and then touch it to the electroscope, the leaves in the electroscope become charged and separate. The experiment demonstrates that like charges repel one another.
the electroscope is made of conducting materials. Because of that, it can be charged by conduction as well as by induction. So in this image, the charged rod is not touching the electroscope. As you can see, it's nearby, but it's not touching. So by induction, the charges on the electroscope and the leaves will split such that negative will be closer to the external rod and positive will be at the other end. Okay? Again, similar charges repel each other, so you have the spread which is proportional to the original outside charge. The other option is touching. So here by conduction, charges will be transferred from the external rod into the electroscope, and again, the spread of the gold leaves is proportional to the amount of charge on this rod. There are other modern electroscopes that are digital, that you just touch them or bring the charged object with unknown charge closer to it, and the digital electroscope will give you the reading that there are that much of charges on this object. Then you can use the electroscope, the charged electroscope, to check on unknown charges. And this answers your question. You said how to tell what kind of charge there. That answers your question. So you start with a charged electroscope, and from the behavior of the leaves, you identify the unknown charges. Like here, if the leaves spread further, then we know the unknown charge is similar, it's negative, while if they spread near to each other, then we know that the external charge is positive. We move on to an important and fundamental law in electricity, in electrostatics, which is Coulomb's law. This guy, Coulomb, lived 1736 to 1806. As you recall, the French Revolution, the Industrial Revolution, was in the 18th century. And at that time, Paris was the center of science and technology. Because of that, electricity, and as we will learn later in magnetism, the most important laws for electricity and for magnetism were discovered by French physicists during that period. Within 30 years, they were able to develop the whole field, and the rules that were discovered during that period are still valid, and we still study them 200 years after that. So what is Coulomb's law? It is an experimental law. It is a law based on observations. Coulomb observed that if you bring two charges near to each other, if they are similar, they will repel each other, and if they are different, they will attract each other. That fact was known before Coulomb. The thing that Coulomb added is to do some measurements on the force, the repulsive force or the attractive force between the two charged objects. He found out that the force on 1 due to 2 is the same as the force on 2 due to 1. And this is consistent with Newton's third law. For each action, there is a reaction equal in magnitude and opposite in direction. So here, if you start with two positive charges, in figure A, they repel each other. If you start with two negative charges, again, figure B, they repel each other with the same force, the same magnitude of the force. However, the action is in one direction and the reaction is in the opposite direction. Then in figure C, if you check the forces. Again, they are equal in magnitude, but opposite in direction, though in this case, they are toward each other, attractive forces. Now, the thing to understand and to remember is the direction of the forces. As you can see in this illustration, the direction of the forces are on the same line. Whether it is repulsive or whether it is attractive, either way, the direction of the forces are on the same line connecting the two charges. Based on observation and measurements, Coulomb found that the magnitude of the force, whether it's F12 or F21, it's the same magnitude. The magnitude is directly proportional with the product of the two charges, Q1 and Q2, and inversely, it is proportional with R squared. In physics, we convert proportionality into an equation form by using a constant. So here, to convert from proportionality to equation form, we use the constant K, and usually the magnitude of this constant is determined from the units. When we study physics, we use SI units, and when we apply SI units for charges, distance, force, the constant K is equal to 8.99 multiplied by 10 to the power 9 in Newton meter squared per Coulomb squared. Sometimes we express this constant, which we call it electrostatic constant, we express it as the reciprocal of 4 pi epsilon naught. This is a convenient form when you want to apply Gauss's law. We will learn more about Gauss's law later in this chapter. Epsilon naught is simply the electric permittivity of a free space, the degree of permittivity or allowance of a free space to electric effect. It's equal to 8.85 multiplied by 10 to the negative 12 Coulomb squared per Newton meter squared. This is called Coulomb's law. If you recall what you learned in Physics 1, try to compare this law to Newton's law of gravitation. What's the difference? In Newton's law, instead of Q1, Q2, you have M1, M2, the first mass multiplied by the second mass. Both laws are called inverse squared law. Inverse squared law. So this is R squared in the denominator. It is not R to the power 1.9. It is not R to the power 2.1 or 2.4, for example. Why it is like that? Nobody knows. Okay? So Newton, for gravitation, did not invent the rule, he discovered it. And Coulomb's here, again, he did not invent this rule, he just discovered this rule by scientific observation. And we know it is valid and it's precise. Of course, knowing the rules allow us to predict behavior of objects and to calculate forces. And this is the main idea behind studying physics. You need to understand this world around you and how to calculate forces and how to deal with things. One point to remember when we talk about Coulomb's law is that this law is about point charges. So Q1 and Q2 are assumed to be point charges. What does that mean? This simply means that the dimensions of Q1 and Q2 are negligible compared to the separation between them. The dimensions of charge Q1 and charge Q2 are negligible when you pair them to the distance r. Okay? So if you try to go to extended objects with dimensions, then obviously Coulomb's law fail. Doesn't apply. It applies only when you have point charges. Now, a few words about the units. In the SI system, the unit of charges was named Coulomb, honoring the guy who discovered this law, Coulomb. And here I'd like to remind you that whenever we deal with a unit derived from the name of a person, we write it with a lowercase letter. So Coulomb, as you can see, starts with lowercase c, while Coulomb, the person, starts with uppercase C, like in the title of this slide, Coulomb's law, uppercase C, because we are talking about Coulomb's, the person. While in the first line of this slide, we are saying Coulomb with a small c, so that you know this is a unit. It's SI unit. It's not the person that we are talking about, but the unit. And in symbol form, in the SI unit, it's uppercase C. Wherever you see uppercase C near a number, to the right of a number, you understand that this number is a charge and it's measured in Coulomb. Force, as you learned in Physics 1, is measured in newtons, and distance is measured in meter. Therefore, it is natural to express K as 8.99 multiplied by 10 to the power 9 Newton meter squared per Coulomb squared. It's common when you solve problems to say just 9 by 10 to the power 9. So we round this 988, we round it, and we say just 9 multiplied by 10 to the power 9. This is good enough for solving problems usually. The Coulomb is a huge amount of charge. Because of that, the unit that is more common in real applications is the microcoulomb. Microcoulomb. As you can see in the last line of this slide, the symbol for microcoulomb is the Greek letter mu before the unit coulomb, C, mu. So 1 microcoulomb is 10 to the power minus 6 of a coulomb. Charges are conserved, as we read last time. And one other important feature for charges is that charges are quantized. Charges are quantized. What does that mean? This simply means there is a fundamental quantity of charge in the universe, and every other charge is an integer multiple of that fundamental quantity. We call that fundamental quantity, we call it the quantum of charge. Quantum of charge. The quantum of charge is equal to 1.6 multiplied by 10 to the minus 19 coulombs. This is the charge carried by 1 electron or by 1 proton. So you cannot find any charge in this universe smaller than this charge. This is the smallest amount of charge, and any other charge is just multiplication of this unit. To bring this concept of a quantization closer to you, think of many other concepts around you that are also quantized. In this auditorium, there are 200 human beings. So what is the quantum of the sample here? 1 human. You cannot talk about half a human or 1/3 of a human. It doesn't make sense. It has to be 1 human, right? And then you have 200 humans in this place. So the quantum of humans is 1 human. Okay? This concept, it's everywhere around us. Okay? So the whole world, you can think of it as discrete. You have quantum, and this quantum repeats. Okay? Chairs. How many chairs we have here? 200 plus chairs. We cannot speak of half a chair or 1/3. It doesn't have any meaning. It has to be one chair, and then repeats. So I hope we get the idea of quantization, because this idea is the milestone of quantum mechanics, which we will learn later in the course. We will come to it later. But for now, we need just to understand that charge is conserved and charge is quantized. Now we will discuss a few examples to illustrate the power of Coulomb's law. In this first example, please read the example. We will apply Bohr model of the hydrogen atom, and the electron rotates in the hydrogen atom in an orbit, and the proton is at the center of that orbit. Hydrogen atom is the simplest atom in the periodic table. The distance between the electron in its orbit and the proton in the nucleus at the center is 5.29 multiplied by 10 to the minus 11 meter. Determine the speed of the electron. So our mission is to determine the speed of the electron in its orbit. I like this example. It is one of my favorite because it allows students to review what they learned in Physics 1 about circular motion. Okay? So to solve this problem, you need two things. First, you need to calculate the force. And to do that, we use Coulomb's law to calculate the force between the two charges. And second, you apply the law for circular motion. This is what we are going to do. So applying Coulomb's law, K, Q1, Q2 over R squared, this is K, and the Q1 and the Q2, each one of them is 1.6 by 10 to the minus 19. We are dealing with the absolute value for the charges. Divide by the distance squared, and here is your answer, 8.22 multiplied by 10 to the minus 8 in Newton. Once you have the force, go to the circular motion equation. Force equals mass by acceleration, and acceleration is written as v squared over r. So now solve for v. From this equation, v is equal to square root of Fr divided by m. The force is 8.22 by 10 to the minus 8 in newtons, r 5.29 by 10 to the minus 11 meter, and the mass for the electron is 9.11 by 10 to the minus 31 kilogram. The answer is 2.18 multiplied by 10 to the power 6 meter per second. These are real numbers. So this gives you an idea about what's going on inside the hydrogen atom. The electron in its orbit around the nucleus in a hydrogen atom is rotating with a speed of 2 million meters per second. This is a huge speed, right? So as an order of magnitude, the rotation speed of electrons around the nuclei, whether it's hydrogen or any other nucleus, as an order of magnitude, you are talking millions of meters per second. A second example about Coulomb's law. Determine the magnitude and direction of the net force on Q1. So we have 3 charges placed on a straight line. Q1 at the center, 3 microcoulomb, it's positive. Q2 to the left, minus 4 microcoulomb. and Q3 to the right minus 7 microcoulomb. We are told that this distance between Q1 and Q2 is 0.2 meter, and the distance between Q1 and Q3 is 0.15 meter. The drawing is not to scale, obviously. Anyway, we are interested in calculating the magnitude and direction of the net force on Q1. Here, I'd like to teach you the method. So please try to pay closer attention. The first step in solving problems is to draw the free body diagram. You know free body diagrams from Physics 1, okay? So identify the object. In this case, the object is a Q1, and then represent the forces acting on it by arrows. So Q1 is positive, Q2 is negative, therefore the force will be attractive. This means that the force will be to the left because Q1 is attracted toward Q2. So this vector, F12, represents the force that charge Q2 acts on charge Q1. Then the other charge is also negative, so the force between Q1 and Q3 is attractive, and therefore we represent it by this vector. You are done. This is your free body diagram. Now all what you need to do is apply Coulomb's law to calculate the magnitude of F12, the magnitude of F13, and then subtract the numbers in order to get the resultant force. So when you apply Coulomb's law, F12, substitute the given values, is 2.7 in newtons, and F13, again, substitute the given values. And I want you to note here that we did not care about the signs. Why? Because we already made use of the signs when we draw the free body diagram. We already made use of the fact that Q2 is negative, Q1 is positive, and so on, when we sketch the free body diagram. So we don't need to worry again about the signs. So when you apply Coulomb's law, you just deal with magnitudes. Excellent. So F12 is 2.7 in Newton, and F13 is 8.4 in newtons. Now, apply vector algebra. Because the two vectors are opposite to each other, you end up with minus 2.7 Newton plus 8.4 newtons. The net force is 5.7 newtons to the right. That is the answer. It's important when you solve problems to use units. Any answer, in general, is a number, and near that number, there should be a unit. Make sure you have the right unit. Obviously, if we are talking forces, then the right unit should be in newtons. Okay, time to check your understanding. Read the problem, and I will start now. So if the separation is tripled, what will happen to the force? Ten seconds to go. 5. Okay. I'm glad that most of you were able to get the right answer. This is very encouraging. So now we know all about this important law, Coulomb's law. We need to learn a little bit about how to apply it. The problem that I solved, 3 charges along the same line, that is the easiest. Sometimes you may face this kind of situation, charges that are not along a straight line. Like in this case, you have 3 charges. So what to do? You need to calculate the force between every 2 charges, represent that force by a vector, and then you need to apply what you learned in Physics 1 for vector algebra in order to find the resultant, as you can see here. You need to apply the superposition principle, okay? So you calculate the force between Q1 and Q2. You calculate the force between Q1 and Q3. In this case, we are interested in the forces on Q3. Q3 is positive, Q1 is negative, so this is the direction of F31. Then Q2 is positive and Q3 is positive, therefore F32 is going this way up. And when you apply vector algebra, this would be the direction of the resultant. In general, we write the resultant using this vector equation. F net equals F1 plus F2 plus F3, whatever. And you need to apply what you learned in Physics 1 in regard to vector addition and vector analysis. This is a quick review. So here if you have this arrow representing force F1 and this arrow representing force F2, in order to find the resultant, you displace this arrow F2, put it here such that the tip of F1 and the tail of F2 are in this shape, and then complete the triangle. So this would be the resultant, okay? Alternatively, try to complete the rectangle, okay? And the diagonal will be your resultant. This is an example that I will leave it for you to practice. I will post the lecture on Blackboard. Usually after I give the lecture, I post it. So please check Blackboard. Lecture 1 already posted. Lecture 2, I will post it today. Make sure to go over the slides. Make sure to understand all the concepts. Lectures are recorded. Go to the student tools. The last icon there is echo. If you click on echo, you will get recording of the lecture in case you'd like to go over the things that we discussed in this lecture. Have a nice weekend and see you next Monday. Take care.